Good morning, friends. I am Dr. Dwivedi again with you, and this is my third lecture. And I'm going to start with the course title, Aircraft Stability and Control, course code AAE 014. I'm going to cover in this lecture, this is the Unit 1, Lecture 3. And before this lecture, I have already completed Lecture 1 and Lecture 2. In these lectures, I have covered about the equilibrium, what is the equilibrium, types of equilibrium, different types of motions which are used for static and dynamic stability. I have also covered the different types of access systems, their basic definitions and directions, and also about static and longitudinal static stability, and this I have already covered. In this lecture, I am going to take on the longitudinal static stability for unaccelerated flight. Hope you will understand and learn this topic in today's lecture. The brief overview of the today's lectures are, I will be covering first introduction, then a basic definition of static stability, then types of aircraft longitudinal static stability, equations of longitudinal static stability, stability derivatives, criteria for longitudinal static stability, primary control derivatives, sign convention for primary control derivatives, examples of control moments, right thumb rule for finding positive and negative moments, cross control derivatives. This will be my last topic. And just I will start with the introduction about today's lecture. In this lecture, the static stability of an aircraft is the first type of stability. As I have already explained in the previous class that we have the static stability and the dynamic stability. So to have the dynamic stable, first it should be statically stable. So the static stability of an aircraft is the first type of stability. Static stability criteria for the three rotational modes, that is rolling, yawing and pitching of aircraft, must be considered separately or individually. They cannot be combined. So I am just only taking in this lecture only longitudinal static stability. The accepted design practice has been to achieve some degree of static stability in each aircraft. Let it be the fighter aircraft or the passenger aircraft or the glider, every aircraft, some degree of static stability is essential and it is very much mandatory. There is two things, that is the stability and maneuverability. So two things we have to trade off needed between static stability and the maneuverability. A combination or a required, as per the requirement of the aircraft, we have to trade off between how much we need static stability and how much we need the maneuverability. High degree of static stability is needed for easy to fly aircraft. To have a very nice and smooth flying and simple flying, a high degree of static stability is required. Fighter aircraft will have low level of static stability so that enhanced maneuverability capability can be achieved. So in fighter aircraft, we need maneuverability. It should be able to perform very high level of maneuverability. So it will have very low level of static stability. But nowadays, due to advent of the fly-by-wire control system, acceptable level of both static stability and maneuverability can be achieved by the help of the computers and by the help of the autopilots. Some degree of static stability in the basic airframe design is intentionally incorporated. So in this, intentionally we put the instability in the design itself to achieve the enhanced maneuvering capability. Static stability concept provide a first step in achieving a design with acceptable flying qualities. So by this introduction, we are very much confident that why we have to study the static stability. So these are all of the point which gives that we have to understand about the static stability. So before I start, I will again repeat the same static stability which I have already covered, but still I need to give some introduction of the previous the class. So in this, static stability is generally defined as the initial tendency of an airplane following a perturbation from a steady state flight condition to develop aerodynamic forces or moments that are trying to return the aircraft to its steady state of condition. So these are the this is the definition of the static stability, and here I have a diagram. In this I have shown the three types of static stability. One is the positive static stability, another is a neutral static stability, and third one is the negative static stability. This is also called the instability. So by this diagram, we can see that the positive static stability, if we take a ball, and in this one ball is there, if you move this ball from one location to the another location, just we can see here, this is the ball which is at the center. If we move this ball here and leave this ball, the intention of this ball is to revert to its original position. So this is called the positive static stability. The second case, if you see here, this one is the trim condition. The ball is at this place at the trim condition. If we move from here to here, this ball will try to remain in this position only. So this is called the neutral static stability. The third case, which is the force resulting from the displacement, if we the ball is here, if we replace from here to here in the new location, you will see that this ball, the tendency of this ball is not to revert to its original position. It is not going in this direction, but it will go away from its new location. It will not revert back to its original position. So it is known as the negative static stability or instability. This is the instability case in which it will not come down to the original position. We have the three types of stability. Okay, so now this you can see types of aircraft longitudinal static stability. We have seen in the previous mechanical example. Now we have to see this thing in aircraft. You can see here, here we have the four diagram. The first one is a trimmed flight in which the aircraft is flying with the alpha 1 angle of attack with a free stream velocity, and the aircraft is flying with steady state. And if due to some alpha perturbation from the trim, just you can see in the diagram that where the arrow is there, this arrow shows that additional increase in angle of attack. Due to the perturbation, maybe due to the gust or some other issues, if the angle of attack is increased, so the nose is up due to the high lift, because once the angle of attack is increased, the lift will also increase. This lift will try to again make the nose up, but due to this, the aircraft will try to come down. As the aerodynamic center is behind the center of gravity, as and when the angle of attack is increased, it means nose is going up, the lift will increase. This lift will try to push down again to its original position, and it is the case of statically stable aircraft. The second case is when the aircraft is flying in a steady state condition and one gust has come, but the nose has gone to its new position and it will remain in the new position. It will not come down to its original position, or the tendency is not coming to its original position. Then and there is no moment produced in this type of case, means in the neutral stable condition, there is no additional moments are produced. The moments which are produced by the help of the gust, that will remain, and the aircraft will fly in the same disturbed condition throughout. So it is called the neutral stable condition. Third one is the statically unstable. In this, due to the aerodynamic center, which is ahead of the center of gravity, the nose will again try to go up only. It will not come down to its original position. So this is called the statically unstable condition. So I have here given this total definition. If a gust produces a perturbation from the trimmed angle of attack and an aerodynamic moment results that would rotate the aircraft back towards the trimmed condition, then we have the positive static stability. If there is no aerodynamic moment results, we have the neutral static stability, and aerodynamic moment results that tends to increase the perturbation, then we have the negative static stability or static instability. So we have these three types of aircraft longitudinal static stability. Now I will go for some equations for the longitudinal static stability. Here we have the terms. The first term is MA, the aerodynamic pitching moment. LA is the rolling moment, and NA is the yawing moment. So this MA is equal to Cm Q bar S C bar, where Cm is the coefficient of moment, Q bar is a dynamic pressure, S is the surface area, and C bar is the mean chord length. Same way for the rolling moment, Cl is the coefficient of rolling moment, Q bar is same as the dynamic pressure, S is the surface area, and B is the span of the wing. And Na is the yawing moment. This yawing moment is equal to Cn Q bar SB, where Cn is the coefficient of yawing moment, Q bar is the dynamic pressure, S is a surface area, and B is a span. So we have defined all the three types of moment with respect to their area and their span or the chord. So in this I am discussing about the longitudinal static stability. So Cm is the longitudinal coefficient of moment, and if we express or extend with the help of the Taylor series, we will get Cm is equal to Cm naught plus Cm alpha alpha plus Cm delta E plus Cm IH. Here because Cm varies with alpha, delta E, IH for steady state trimmed condition. So again, this is the continuation of this. The same equation is depicted. So here alpha is the angle of attack, delta E is the elevator deflection, IH is the incidence angle of the horizontal stabilizer, the angle between the horizontal stabilizer chord line and the fuselage reference line or X body axis, defined as positive for leading edge of deflection. Cm naught is the value of the Cm when alpha, delta E, IH are equal to 0. So in this, Cm naught is the trimmed condition at which the all angles, including angle of attack, even this elevator angle or the tail plane fixed at the 0, then it is called the Cm naught. Similarly, the rolling moment coefficient Cl is equal to Cl naught plus Cl beta plus Cl delta A into delta A plus Cl delta R. And the same way, the yawing moment coefficient Cn is equal to Cn naught plus Cn beta plus Cn delta A plus Cn delta R. So here, I think we all know that what is the angle of attack. I have just here explained about the beta, because this beta is side slip angle, and this side slip angle is the angle between the relative wind and the X body axis in the XY plane as shown in the figure. You can see in the diagram that if the aircraft is flying in a X direction and it moves towards the right, then it is called the plus beta. So the relative wind and the axis of the aircraft in the horizontal plane, it is called the plus beta. Here this delta A is the aileron deflection, not elevator. A always indicate about the aileron and R is always the rudder. So del R is rudder deflection. CL naught and CN naught are the values of coefficient of rolling and coefficient of yawing moment respectively when beta, delta A and delta R equal to 0. For symmetrical aircraft, CL naught and CN naught are usually 0. So if we are testing any symmetrical aircraft wing, then it is CL naught and CN naught will always be 0. So we can calculate like this. Next, we have to go about the stability derivatives. So here we have in the previous equations, we have the Cm alpha, Cl beta and Cn beta are referred to as a stability derivatives. They represents the change in applicable moment coefficient with respect to the change in direction of the relative wind, that is alpha for longitudinal motion, beta for lateral and directional motion. So Cm alpha, Cl beta, Cn beta, they are the relative with respect to the coefficient of moment of in the longitudinal, coefficient in the this lateral and coefficient of moment in the yawing direction. So it is always, we have to understand this terminology. The sign of each of these derivatives will determine the longitudinal, lateral and directional static stability respectively of an aircraft. So here you can see in this diagram I have shown about the longitudinal static stability. In this Cm alpha, the derivative Cm alpha is represented. This Cm alpha is equal to dCm by d alpha. If you see this diagram, I have plotted here the Cm versus alpha, and Cm naught is the coefficient of moment at 0 angle of attack, and this is here shown positive. So if the Cm naught is positive and the dCm by d alpha is going negative, then it is a statically longitudinal stable aircraft. So this figure presents a negative slope of Cm versus angle of attack. The slope is change in Cm divided by change in angle of attack. This is called the stability derivative Cm alpha. Criteria for the longitudinal static stability. When we have to say that aircraft is longitudinal stable, statically stable. So in this, with Cm alpha negative, in this your Cm alpha should be negative. There are, in this we have the two conditions. First one is the Cm should be greater than 0 or positive, and dCm by d alpha, that is Cm alpha, should be less than 0 or the negative. Then the aircraft is statically longitudinal stable. With Cm alpha negative, notice that a gust that causes a perturbation in trim of the angle of attack to a slightly lower value results in a positive aerodynamic pitching moment, which gives the aircraft an initial tendency back towards the trim condition. Likewise, a gust that causes a perturbed increase in angle of attack will result in a negative pitching moment, which also gives the aircraft an initial tendency back towards the trim condition. Thus, a negative Cm alpha can be seen as the requirement for the longitudinal static stability. So if Cm alpha is negative, then we can assume that the aircraft is longitudinal static stable. Primary control derivatives. So in this, we have the Cm delta E, Cm IH, Cl delta A and Cn delta R are referred as the primary control derivatives. These are also known as the control power. Here we have the first one is the Cm delta E is the longitudinal control power or longitudinal control derivatives that defines the change in coefficient of moment, that is Cm, that results from in change in elevator deflection delta E. The higher the absolute value of a control derivatives, the more moment is generated for a given control deflection. One could think of this as a higher control sensitivity for a given moment of inertia. So if the value of Cm delta E is positive, or the number of this thing is positive, then it is a higher control sensitive. It means it generates more moment, and the direction, if it is negative, then it is a statically stable condition. Sign convention of the primary control derivatives. Here I have just explained about the what type of sign they are positive and which type of they are the negative for the control derivatives. The positive elevator deflection, when the delta E is trailing, is down. If you see this aircraft, this is the elevator, this is the elevator. If this elevator, this thing is down, then it is called, it is a positive elevator deflection. If it is like this. So if you are putting like this, what will happen? In this, angle of attack is increased. The forces which are generating here, this will be more. So this aircraft, if it is flying like this, and it will put down the aircraft in this way. So positive elevator deflection is trailing edge down. So when the trailing edge, this is called the trailing edge of the elevator. So when the trailing edge you are putting down, it will try to pull up the backward side and the nose will go down. So this is the called the positive elevator deflection. Then positive incidence angle of the horizontal tail. You can see this here. This is called the horizontal tail, and this is the here IH. So with respect to the center line of this aircraft, angle of your this chord line of this and the angle of this, it is called the horizontal stabilizer angle. The positive incidence angle of the horizontal stabilizer is leading edge up. This is the leading edge. So if this leading edge is in this direction, it is a positive tail. So positive incidence angle of the horizontal stabilizer. Now the positive aileron deflection is trailing edge on the either of aileron, and a composite aileron deflection dA is defined as the difference between the left aileron deflection and the right aileron deflection divided by 2. So delta A is equal to half delta A left minus delta A right. So it is the left. So if it is the left is down, so right will be up. So this down minus this right up divided by 2, this will be a delta A. So in this, what is the sign convention of the rudder? So in this positive rudder deflection, the delta R is the trailing edge left. So if this is the straight, the rudder is straight, if you are deflecting towards the left like this, then it is a positive. And if you are deflecting like this, then what will happen? The wind will go from the here, the angle of attack is increased, it will try to pull towards this, towards the right. So nose will go towards the left. So nose left is your positive rudder deflection. So in this way, all the 3 controls are defined with respect to the their convention. So the nose left is the positive, and nose down is positive, and left roll is positive. So all these 3 we have to take the positive deflection. Examples of the control movements. I have just, for a positive elevator deflection, delta E will typically result in a negative nose down pitching moment. For a positive elevator deflection means if you are putting the elevator down, typically result in a negative nose down pitching moment. So if you are putting down, aircraft will be nose down. So if it is like this, it is a positive. A positive IH will typically result in a negative pitching moment. If the angle of attack of this or the angle of incidence of the tail plane is positive, means the leading edge is upward, then it is also typically a negative pitching moment. Your aircraft will go, nose will try to go like this. A positive aileron deflection will typically result in a positive right wing down. So if it is positive, your right wing will be down, rolling moment. So if the right wing is like this, it is a positive rolling. A positive rudder deflection will typically result in a negative nose left. So if it is positive like this, the aircraft will be rolling like this. Now, these all things, there is a rule, it is called the right thumb rule for the finding positive and the negative moment. If the right thumb is placed along the elevator hinge line, pointing in the direction of the positive y-axis, just you can see, this is the thumb and it is placed in the elevator. Then in y-axis, the finger curl is the trailing edge. So it is going down, means your trailing is going down. It is defined as the positive. A similar argument can be made for the ailerons. Here, for the rudder, the right thumb is pointed towards the direction of the earth. Okay, like this. Then you can see that the curling of this will give you the positive, this angle of attack, and it is a positive derivatives. So in this we have the, if the Cm delta is negative, if Cm delta E is negative, Cl delta A is positive, and the Cn delta R is negative, because the control surfaces sign convention for a specific application external to this text may be defined. So to have a positive longitudinal, it should be negative. For the longitudinal static stability, Cm delta E should be negative. For the rolling stability, Cl delta A should be positive, and for the yawing moment, Cn delta R should be negative. So these are the three primary this derivatives, and this should be positive or negative. As per that, we can define that whether it is stable or not stable. Now, next is the cross control derivatives. Previously, we have discussed about the primary control derivatives. Now it is a cross control. It means you apply something else and happening something else, like Cl delta R and Cn delta A are called the cross control derivative because they define the change in moment that results from the change in a control surface. That is not primary control surface for that axis. So for example, Cl delta R defines the change in rolling moment that results from a change in rudder deflection, with the aileron being the primary control surfaces for the roll axis. Just you can see here that in this aircraft, when I am applying this rolling moment, so this rolling moment will be with the help of the aileron. So if I am applying this, rudder will also take some action. So rudder is also required. So both in the rolling and the yawing, both are the cross controlled. It is called the cross control. Means to make your wing one side rolling, you need to apply the rudder also. So CLR defines the rolling moment then that can be generated with non-primary control surfaces. It means if rudder is not there, you can operate the aircraft with the help of the aileron. Or if ailerons are not there, you can use the rudder and you can operate the aircraft to operate. So this both are the complementary. So they are called the cross control. Means rudder and aileron each can be deflected and their results can be achieved. So I have completed this lecture today, but in the next topic I will be covering the longitudinal applied forces and moments, aircraft drag, aircraft lift, aircraft pitching moment, Cm0, Cm alpha, CMIH, CMDE, and aerodynamics center. And next class I will be handling in my lecture 4. These all topics I will be covering with some derivations also. Thank you very much for this class.
like, share, and subscribe. Hit the bell icon for more updates.